Welcome back to the decision tree module. In the previous videos, we've seen that attribute class is able to estimate the student's behavior about playing cricket or not, and this attribute is doing a much better job compared to the remaining two variables like the height and the performance in the class. If you recall, we made the split on all the available features and then compared each split to decide which one was the best. That is how the decision tree algorithm also works. It first splits the nodes on all the available variables and then selects the split which results in most homogeneous subnodes. Homogeneous here means having similar behavior with respect to the problem that we have. If the nodes are entirely pure, each node will only contain a single class and hence they will be homogeneous. So intuitively, you can imagine that more the purity of the nodes, more will be the homogeneity. There are multiple algorithms which are used by decision tree to decide the best split for the problem. Let's first look at the most common and popular out of all of them, which is Gini impurity. It measures the impurity of the nodes and is calculated as 1 minus Gini, as you can see in this slide. Let's first understand what Gini is, and then I'll show you how you can calculate the Gini impurity for splits and decide the right split. Let's say we have a node like this. So what Gini says is that if we pick 2 points from a population at random, the pink ones highlighted here, then they must be from the same class. Let's say we have a completely pure node. Can you guess what would be the probability that a randomly picked point will belong to the same class? Well, obviously it will be 1, since all the points here belong to the same class. So no matter which 2 points we pick, they will always belong to that one class, and hence the probability will always be 1 if the node is pure. And that is what we want to achieve using Gini. Gini ranges from 0 to 1 as it is a probability, and the higher this value, more will be the purity of the nodes. And of course, a lesser value will mean lesser pure nodes. Let's look at the properties of Gini impurity before we actually calculate the Gini impurity to decide the best split. We decide the best split based on the Gini impurity. And as we discussed before, Gini impurity is 1 minus Gini. Here Gini denotes the purity, and hence Gini impurity tells us about the impurity of nodes. Lower the Gini impurity, we can safely infer that the purity will be more, and hence a higher chance of the homogeneity of the nodes. Gini works only in those scenarios where we have categorical targets. It does not work with continuous targets. Very important point to keep in mind. For example, if you want to predict the house price or the number of bikes that have been rented, then Gini is not the right algorithm. It only performs binary splits, either yes or no, success or failure, and so on. So it will only split a node into 2 subnodes. These are the properties of Gini impurity. Let's now look at the steps to calculate Gini impurity of a split. First, we calculate the Gini impurity for subnodes. As we've already discussed, Gini impurity is, and I'm sure you know this by now, 1 minus Gini. Here Gini is the sum of squares of success probabilities of each class and is given as P1 square plus P2 square and so on till Pn square, considering that there are n classes. Once we've calculated the Gini impurity for subnodes, we calculate the Gini impurity of the split using a weighted impurity of both subnodes of that split. Here the weight is decided by the number of observations or samples in both the nodes. Let's look at these calculations using an example which will help you understand this even better. For the split on the performance in the class. Remember, this is how the split was. We have 2 categories. One is above average and the other one was of course below average. When we focus on the above average, we have 14 students, out of which 8 play cricket and 6 do not. The probability of playing cricket would be 8 divided by 14, which is around 0.57. Similarly, for not playing cricket, the probability will be 6 divided by 14, which will be around 0.43. Here for simplicity, I've rounded off the calculations rather than taking the exact number. Similarly, when we look at below average, We calculated all the numbers and here they are. Probability of playing is 0.33 and of not playing is 0.67. Let's now calculate the Gini impurity for the sub-node for above average. And here's the calculation. It will be 1 minus square of probability of success for each category, which is 0.57 for playing cricket and 0.43 for not playing cricket. So after this calculation, the Gini impurity comes out to be around 0.49 for this above average node. We'll do the same calculation of Gini impurity for below average. It comes out to be around 0.44. If you want, you can pause the video here and just analyze these numbers and plug them in yourself. Now to calculate the Gini impurity of the split, we will take the weighted sum of Gini impurities of both nodes, above average and below average in this case. The weight of a node is the number of samples in that node divided by the total number of samples in the parent node. So for the above average node here, the weight will be 14 by 20, as there are 14 students who performed above average out of the total 20 students that we had. And the weight for below average is 6 divided by 20. So the weighted Gini impurity will be the weight of that node multiplied by the Gini impurity of that node. The weighted Gini impurity for performance in class split comes out to be 0.475 after we perform this calculation. Similarly, here we have calculated the Gini impurity for the split on class, which comes out to be around 0.32. I strongly recommend you to do these calculations on your own and then come back and match your values with the ones that we have shown in this slide. Now, if we compare the two Gini impurities for each split, we'll see that the Gini impurity for the split on class is less. And hence, class will be the first split of this decision tree. Similarly, for each split, we will calculate the Gini impurity, and the split producing minimum Gini impurity will be selected as the split. And you know that minimum value of Gini impurity means that the node will be more pure or more homogeneous. We already discussed this. In the next video, we'll look at another method that is used to decide the best splitting point, which is chi-square. It's a very interesting video and I'll see you there. Thank you.